Welcome to the final exam review part 2. What is the Kelvin temperature that is equal to 25 degrees Celsius? Okay, well, Kelvin is the scale based on absolute zero. Zero Kelvin is the lowest possible theoretical temperature, and that's equal to negative 273 degrees Celsius. So if you want to convert from Celsius to Kelvin, it's plus 273. 25 plus 273 is equal to 298 Kelvin, which is choice B up here. As ice cools from 273 Kelvin to 263 Kelvin, so it's getting colder, what happens to the average kinetic energy of the molecules? Well, temperature is a measure of the average kinetic energy. So if we decrease the temperature, that means we are decreasing the kinetic energy of the molecules. Or you could look at it the other way around and say, as the kinetic energy gets lower, the temperature goes down. They're sort of interchangeable like that. So the answer here is that the kinetic energy goes down, decreases. What is the mass of 0.5 moles of calcium phosphate? So you would need to look at the periodic table for this. All right, so we've got calcium on the periodic table has a mass of 40. And according to the formula, there are 3 of them. So we're going to multiply that number times 3, which is 120. The phosphorus, which is in the parentheses here, has a mass of 31 on the periodic table. The little 2 outside the parentheses here tells me that there are 2 of those. So that's 62. And then finally, over here we have oxygen, which has a mass of 16. There's 4 in the parentheses times 2 outside the parentheses, so we're going to multiply 16 times 8, and that gives us 128 for all the oxygens. Then we simply add these all together, and we get a mass of 310. Let me add that together. That would be 1 mole. The question is, how much does half of a mole weigh? So we would just multiply that by 0.5, and we get 155 grams, which in scientific notation is 1.55 times 10 squared. What is the empirical formula of glucose? Well, remember, the empirical formula is the simplest ratio. So we divide all the numbers in the formula by the biggest number that goes into every one of the numbers. Well, 6, 12, and 6 can all be divided by 6, which would leave us with C1H2O1. And in formulas, we don't write the 1. So the formula that would fit that would be CH2O. That's the simplest ratio of the elements in the compound, even though it's not actually the number of each element in the compound. That's what the empirical formula is. If we have a balloon at a constant pressure with a volume of 120 milliliters at a very cold temperature of 123 below 0 Celsius, what would its volume be if we raise the temperature way up? Well, this is one of the gas laws. All right, volume over temperature initial is equal to the final volume and the final temperature. Key thing to remember, always change your temperatures to Kelvin. So the first volume is 120 milliliters, and the temperature 123 Celsius below, negative 123 Celsius, plus 273 to get it into Kelvin, gives us 150 Kelvin. So that's the starting conditions. Then we change the temperature, we raise it up to 27 Celsius. 27 plus 273 is 300 Kelvin. And the question then is, what's that final volume? So proportion, you set it up, you cross multiply, you end up with 240 milliliters. And that actually kind of makes sense. If you look down here, the temperature in Kelvin doesn't look like that in Celsius, but the temperature in Kelvin doubled times 2, which means that the volume should double which it did, 240 milliliters. How many moles of N2 are in a flask with a volume of 2.5 liters at standard temperature and pressure? So anytime you're dealing with gases and the number of moles, you're using what's called the ideal gas law. The pressure times the volume equals the number of moles times the ideal constant R times the temperature. Again, temperature is going to have to be in Kelvin. Well, they didn't give us a temperature, a number for temperature, and a number for pressure. They said standard temperature and pressure. So you need to know that standard temperature is 273 Kelvin. That's temperature. Standard pressure is 1 atmosphere. Okay, there's other ways to measure it, but we're going to use atmospheres because that's the easiest one. All right, so we're given volume, pressure. Right, pressure is 1.0 atmospheres. Volume is 2.5 liters equals the number of moles, which we're trying to find, times the ideal gas constant. That's what R stands for. And when the ideal gas constant is for a unit of atmospheres, which is what we used, the number is 0.0821, and then times the temperature. Standard temperature is 273 Kelvin. So if we solve for N, what we're going to do is we're going to divide both sides by the 0.0821 times 273, and that leaves us with N equal to 0.112 moles. And you could have done the multiplication over here and the multiplication over here first and then divided by the answer. That's fine. The order in which you do those steps doesn't really matter. All right. In an aqueous solution, the chloride ion is attracted to which end of a water molecule? All right, so a couple things you need to know here. Chloride. Chlorine ion has a charge of -1. It's a halogen. All the halogens have a charge of -1 when they make an ion. So then the other part is, well, what are we talking about the ends of the water molecule? Well, a water molecule looks sort of like this. It's got the oxygen in the middle, the hydrogens on either side, and then it's got these lone pair electrons up here. So because the hydrogens are down at the bottom in this drawing, and the electrons are up here at the top, and because the oxygen is going to pull away hydrogen's electrons, the top end, again, this end of the molecule, the oxygen end, is very negative. Not an ion, but it's very negative. The hydrogen end is very positive. So the negative chloride is going to be attracted to the positive side of the water molecule, which is the hydrogen side. So that's choice A. Okay, 100 grams of water with ammonium chloride at 50 degrees Celsius. According to the solubility curve, the temperature is lowered to 10 degrees Celsius. How much ammonium chloride will precipitate out? So you just jump back real quick to the solubility curve. So it's 50 degrees down to 10 degrees of ammonium chloride. So here we go. Here's the chart. Here are these lines that are here, and we're looking at the ammonium chloride, and we're going from 50 degrees down to 10 degrees. Okay, so if we look at the lines, at 50 degrees we're looking at roughly 50 grams of ammonium chloride, and then at 10 degrees we're somewhere between 30 and 40. So we've lost between 10 and 20 grams that will precipitate out. So somewhere roughly around 15 is what we're looking at. The closest one here would be 19. Okay, that's the closest to 15 of these answers. So when you lower the temperature, not as much solute can be held in the solvent, and then you just have to kind of follow the arc of the solubility curve to find the difference between the starting temperature and the final temperature. That difference in those two numbers is how much will precipitate out. In a potential energy diagram, the difference between the energy of the products and the energy of the reactants will be equal to. So earlier, when we were talking about the activation energy, there's a chart or a diagram that looks sort of like this. This is what a reaction, the energy in a reaction looks like. Over on this side, we have reactants. Okay, in the middle, we have this activation energy, which all the reactants have to get over in order to turn into the products. And there are lots of different energy curves that we could draw. This one, in this case, the energy. So the energy is going up, okay, as you move up on this graph, and moving down as you move down in the graph. So in this case, the difference between the reactants and the products is this gap here. Not the activation energy, but the gap between the reactants and the products. Okay, so what happens is, if you have a difference between reactants and products, that means you have a difference in energy. That energy has to go somewhere. In this case, since the products are lower, the energy is going to get released as heat. If the products were up higher, it would be absorbed as heat. So that's what we call the difference between exothermic, heat being released, and endothermic, which is heat absorbed, is all about, well, what's the relationship between the height of the reactants and the height of the products on this energy curve. Higher reactants means exothermic because you're going to have less energy in the system at the end. Lower reactants and higher products means it needs energy to get up to that level. But overall, the change in energy, whether it's in or out, is called the heat of the reaction. If I take 0.15 molar solution and I have 5 milliliters of it, I dilute that down to 5 liters. What is the final concentration? Well, the dilution equation is the starting molarity times the starting volume will be equal to the final molarity times the final volume. So then I got to plug in the numbers that I'm given, and I got to make sure that they're in the same unit, since the volume here is in 2 different units. So it doesn't matter if you convert to liters to milliliters or milliliters to liters. Either way, you're moving the decimal 3 times. So 0.15 molar solution, I'll convert this to liters, is 0.005 liters, which means the final molarity times 5 liters is the concentration, the answer we're given, or we're looking for. So we divide these two things by 5, to cancel that out, and we end up with 0.00015 molar. Okay, it's a really small concentration, but when you think about it, you're taking 5 milliliters and you're diluting it 1,000 times. So yes, it's going to make sense that the concentration goes down because you're adding so much more water that you're spreading out all those particles and it's getting more dilute. Which of the following has the highest concentration of hydrogen ions? Remember, concentration of hydrogen ions as it goes up when we're looking at pH. So pH goes down as hydrogen ions go up. So if we want the highest concentration, we want the lowest pH. So the lowest pH, 13.743, well, that would be vinegar. Vinegar with a pH of 3 is the most acidic, which means it has the most hydrogen ions out of these 4 choices. We've got a reaction, we've got an equation. Which reactant is the Bronsted-Lowry base? So again, remember in the Bronsted-Lowry definition, acid equals proton donor. It means it's going to give up a hydrogen. And base is hydrogen or proton acceptor or receiver or consumer. However you want to think about it, it's the thing that takes the hydrogen. One thing gives up a hydrogen, that's the acid. The other thing gets the hydrogen, that's the base. So how do we figure that out? Well, look at the equation. Which thing has more hydrogen on the right than it did on the left? That's kind of the simplest way to look at it. Well, the HI actually has less hydrogen on the right because it's just I. The H2O has now become H3O, so it gained the hydrogen. We're looking for the base. The base is the thing that gains the hydrogen, which means the water is the acid. Not the H3O, that's already gained it. Okay, so that's after the reaction. The acids and the bases are always the stuff on the left. The stuff on the right is what are called the conjugate acids or conjugate bases. In an unsaturated solution, what's an unsaturated solution? We've got unsaturated, saturated, supersaturated. Unsaturated means it has not yet dissolved the maximum amount of solute. So that's choice A, right? So that's unsaturated. If it has dissolved the maximum amount, that's called saturated. And then the last choice here, it's holding more, it's unstable because it's holding more than it should. That's called supersaturated. Which of these phase changes would be accompanied by the release of heat? And we don't really think about it this way, sort of in our experience, because we look at it from a different perspective. But the heat, or release of heat, or release of energy, you have gases, you have liquids, and you have solids. When you compare them, the energy goes down as you go from gas to liquid to solid, or it goes up from solid to liquid to gas, however you want to look at it. But we're looking at the release of heat, which means we're losing energy. So we're going down from gas to liquid, liquid to solid, or gas to solid. All three of those combinations can take place. So which of these has either gas to liquid, liquid to solid, or gas to solid? Because it's got to be one of those. Well, the first one is solid to liquid. That's going the wrong direction. The second one is liquid to solid. So that fits going from liquid, which is higher energy, to solid, which is lower energy. You have to release that energy. It has to go somewhere, and we call that the release of heat. The other one is solid to gas or liquid to gas, which are both going up instead of down. If a compound has a pH of 6.5, what is its pOH? Well, this one is based on a very simple fact that pH plus pOH always equals 14, which means that 14 minus 6.5 in this case equals the pOH, which means that we've got a pOH of 7.5. What is the pH of a 0.002 molar solution of hydrochloric acid? Okay, so we've got hydrochloric acid, which has hydrogens. It's a strong acid, which means that we can use the concentration of the solution as the concentration of hydrogen ions, 0.0020. And the pH is found by taking the negative of the log of the hydrogen ion concentration. So the negative of the log of 0.002 is 2.698. When we round that for significant figures, we get 2.7. So that would be the pH.